Welcome to the deep dive. You know, we're often promised this kind of AI that solves the world's toughest problems.
Oh, absolutely. The pitch is always about drug discovery, personalized medicine, real-time clinical diagnosis.
And it's always framed around this idea of a giant, all-knowing generalist AI.
But the reality, well, when you actually put these systems under real scientific or commercial pressure, the picture changes. They're often brittle, unpredictable.
And surprisingly bad at just fundamental scientific rigor.
Exactly. The challenge isn't really about making AI smarter in the abstract. It's making it trustworthy.
Absolutely. When you're talking about regulated industries, a patient's life, a massive financial risk model, you just can't have guesswork. You can't have random output.
And that idea of trust, it really boils down to three core pillars that modern LLMs and vision language models are really struggling with.
Okay, what are they?
Reproducibility, structural reliability, and just basic robustness.
So today, we've got sources that hit all three of those. We have reports on medical VLMs, trying to read complex 3D scans, deep dives into knowledge graph extraction, and even these new frameworks for multi-agent clinical consensus.
And they all point to the same conclusion, really. The future of high-stakes AI isn't some single monolithic model.
It's specialized, verifiable systems built on rigor. And our mission today is to figure out how researchers are stitching that rigor back into systems that were, let's be honest, designed to be a bit fuzzy.
It's a fascinating problem, a mix of pure computer science and just practical scientific necessity.
Okay, let's unpack this then. And let's start with the most fundamental demand of science, of industry, really. Just getting the same answer twice.
Right, which takes us straight to the problem of non-determinism. And for anyone listening who hasn't run into this, imagine asking your AI a critical question.
Like a risk assessment.
A risk assessment. It's a diagnostic suggestion, whatever. And then you ask it again 5 minutes later. Same data, same model, and you get a slightly different answer.
That would be a nightmare. In clinical research, reproducibility is everything. If the AI just, changes its mind, how do you even begin to audit that?
You can't. It's a complete deal breaker for any serious enterprise adoption. And this was a huge, persistent problem for LLMs.
So what was causing it?
It all comes down to how these massive models process information. During inference, when it's generating an answer, it's doing billions of matrix multiplications.
It's a huge calculation.
Huge. And to be efficient, the system parallelizes that work. But the exact path the data takes through the hardware can change, especially depending on the batch size.
The batch size. So how much data is being processed at once?
Exactly. And when that batch size varies, or even how it's laid out in memory, you get these tiny, tiny floating point variations in the math.
And in a model with trillions of parameters, I imagine those tiny variations they must just explode.
They compound, precisely. And that results in a slightly different word, a different token being chosen at the end. That's your randomness.
So what was the fix? Some new complex algorithm?
No, and this is the brilliant part. It was just clever engineering. They found that by standardizing the batch size variability during inference, they could force the exact same computational path every single time.
So, same input, same path, same output.
Every time. It was a huge victory for engineering control over, that inherent randomness.
A massive step for consistency. But consistency only gets you so far if the answer is consistently wrong. Which brings us to structural reliability.
And this really gets at the two big paradigms in AI. You have the old guard, the symbolic system.
The rule-based stuff.
Exactly. Perfect for rules, great for interpretability. You know exactly why it made a decision, but they break when the data gets messy or you need to scale up.
And then you have the new guard, neural learning, the LLMs. They are incredible at finding patterns in huge, messy data sets.
But they're black boxes. Their knowledge is implicit, and they are, as we all know, very prone to hallucination. They'll generate these confident, fluent, and just completely false statements.
Okay, wait. So if you try to combine them, this idea of neurosymbolic AI, aren't you just risking getting the worst of both worlds?
That is the tension, but the vision is to get the best of both. You let the neural network do what it's good at, learning from noisy real-world data, but you force it to ground its reasoning in a symbolic system and explicit auditable framework of facts.
And the best structure for facts is a knowledge graph, a KG.
Right, where knowledge is broken down into simple triples, like metformin, treats, type 2 diabetes. It's explicit, you can check it, you can audit it. It's what LLMs are missing.
But the problem comes when you try to use an LLM to build that knowledge graph from, say, thousands of medical journals.
That's where it all falls apart again. Our sources show that LLM-based KG generation is just It's super unreliable. It hallucinates, it injects irrelevant noise, especially with domain-specific data.
Can you give us an example? What does that failure actually look like?
Sure, so imagine an LLM is reading a medical paper and needs to extract a fact like chronic kidney disease has finding site. That has finding site relation needs to point to a very specific anatomical structure.
Okay.
An LLM, just going on general language patterns, might fill that in with a generic location or something completely non-anatomical. It doesn't understand the strict symbolic meaning. And worse, it doesn't tell you where it got that idea. There's no source attribution.
Which is useless if you're building a verifiable fact base. I mean, the numbers in the study were shocking. The LLM baseline only got a FAST score of around 40%.
Meaning it was just guessing about 60% of the time.
So what's the alternative?
A framework called GraphMERT. It's a transformer that's specifically designed for this one job. It's not a generalist. It takes a small amount of high-quality text and a small seed of a trusted KG.
And it builds out from there, prioritizing quality over quantity.
Exactly, and the results are just night and day. GraphMERT achieved a FACT score of nearly 70%. That huge gap shows the difference between guessing and rigorous, structured extraction. It's an argument for deep, domain-specific superintelligence over broad, general AI.
So getting the structure right is non-negotiable. Let's shift to another problem then. Brittleness and generalization, especially in a field like medicine. We're now seeing vision language models, VLMs, being used for things like reading MRI scans.
And again, they show this kind of impressive general understanding, but they stumble on the fine-grained, structured tasks that clinicians actually perform.
Like assessing osteoarthritis in a knee from an MRI.
Right. A clinician follows a very specific workflow, something like the MOAC system. It's region first.
Walk us through that. What does a region-first workflow actually involve?
Well, a human expert doesn't just glance at the whole scan. Step one is localization, pinpointing a very specific subregion like a compartment of the knee cartilage in that 3D volume.
Okay, so you find the spot first.
Then step two is assessment, checking that spot for abnormalities. And step three is grading, assigning a severity score. The VLM has to do all three, and the researchers found that step one, the localization, was the biggest hurdle.
That's fascinating. So it's not the high-level reasoning, it's the low-level perception that's failing.
Precisely. And here's the kicker. When the researchers basically gave the VLM the answer to step one, when they gave it the ground truth region in the prompt,
They just pointed it to the right spot.
they pointed it to the right spot, and suddenly its overall diagnostic accuracy jumped significantly. The model's reasoning about severity and its use of medical knowledge was there all along, but it was being crippled by its own visual imprecision.
That weakness highlights this huge challenge of generalization. And when we talk about generalization, we have to talk about data leakage, which brings us to drug discovery.
Yes. For years, AI models that predict molecular binding affinity, a really key step, were posting these amazing performance scores. Turns out a lot of that performance was an illusion.
An illusion created by train test data leakage.
Which is when the model essentially gets to see the answers to the tests during training because the training data and the test data are too similar.
It's not learning to predict, it's learning to memorize.
Exactly. Researchers found huge structural similarities between the PDBB bind training set and the CASF benchmark test set. The models were just recognizing things they'd already seen.
So how on earth do you fix a problem that's contaminated an entire benchmark for a field?
Well, a team had to go in and create a whole new filtered data set. They called it PDB bind clean split. They used an algorithm to systematically kick out any training examples that looked too much like the test examples.
Forcing the models to actually generalize for real.
Right. And what happened when they reran the experiments?
Let me guess. The scores plummeted.
They dropped dramatically. For models like PAFNAC and GenScore, it confirmed their high scores were heavily inflated by that leakage. It's a massive finding because it means a lot of high-profile models weren't creating new predictive power. They were just very good filing cabinets.
That focus on rooting out shortcuts is so critical. And it leads us perfectly to our final segment. What happens when you address this brittleness head-on with the power of a second opinion?
Before we get to the solution, it's worth highlighting just how fragile these single, powerful models can be under stress tests. They rely on these incredibly brittle shortcuts.
Okay, the sources gave two great examples. Let's start with the first one. Option substitution.
Right. So in a multiple choice question, the researchers would take one of the wrong answers, a distractor, and just replace it with the word unknown.
And what happened?
The model's accuracy consistently went up, by 5 to 8 percentage points.
Wait, up. Why?
Because the model didn't treat unknown as a signal to say, I'm not sure. It just saw it as a really weak wrong answer, making it easier to guess the right one from the remaining choices.
So it's not demonstrating uncertainty, it's just gaming the test.
Exactly. And the second example was even more damning. It involved a visual shortcut.
What did they do?
They took a question, but they swapped the input image for one that supported a different, incorrect answer. The text of the question stayed the same, and the model's accuracy just collapsed, dropped by over 30 percentage points.
Wow. So it proves the model wasn't really reasoning between the image and the text.
Not at all. It was relying on a brittle pairing. If I see this kind of image, the answer is usually C. You break that pairing, the whole system falls over.
And that instability is exactly why something like the consensus mechanism, or MEDCON-1, was created. It's a framework that simulates a hospital's tumor board.
Instead of one superstar AI, you have a panel of specialized expert agents.
And does this digital board meeting actually work better than one single super powerful AI?
Oh, consistently. MEDCON-1 significantly outperformed leading single models with a big accuracy jump on a really tough benchmark called MedExpert-QA. But the real win wasn't just the average score. It was minimizing the catastrophic failures. A single model might be great at cardiology, but terrible at, say, nephrology. The ensemble gives you a much more robust, evenly competent performance across the board.
What's really interesting is that it's not just a simple vote. Each expert agent has to return a full probability distribution.
Yes, this is key. It captures their uncertainty. It's not just the answer is A. It's I'm 60% sure it's A, but there's a 30% chance it's B.
And they had a fantastic case study for this with a patient with a deep vein thrombosis, a DVT.
A really complex case. The patient had just had brain surgery, a craniotomy, but also had severe kidney failure. They needed treatment for the blood clot, but standard blood thinners were incredibly risky.
Because of the bleed risk in the brain.
Exactly.
Yeah.
So you have these competing high-stakes trade-offs. The hematologist agent, noting the kidney failure, suggested a specific kind of heparin that's safer for the kidneys.
Okay.
But the vascular surgeon and neurosurgeon agents, they were much more worried about the brain bleed. They strongly recommended an IVC filter, which is a device that physically catches the clot.
So the final consensus model had to weigh those conflicting expert opinions.
And it didn't just average them. It reasoned through the constraints, the recent surgery plus the kidney failure, and it concluded that the IVC filter was the best path because it minimized the most immediate life-threatening risk. It's a layer of reasoning, not just adding up probabilities.
That is genuinely fascinating. It's modeling the actual complexity of a multi-specialty consultation. It's not a poll. It's a system for articulating judgment.
And that articulation is the whole game. That's trust.
So when we step back, what we've seen across all these sources is that when you push AI into these high-stakes fields, you're forced to confront all its flaws. Non-determinism, implicit knowledge, these brittle shortcuts.
And the solutions, they all point in the same direction. They point towards integrating rigor back into the core of the system. Guaranteed output, grounding in knowledge graphs, using ensembles to simulate expert consensus.
It really feels like a new level of maturity for AI. And the biggest benefit isn't just a higher score on a benchmark. It's that ability to provide a transparent, probabilistic look at uncertainty.
Right. It allows the AI to finally function as a true support system, one that knows what it doesn't know, instead of a replacement that demands our blind faith.
Which leaves us with a final provocative thought for you to consider.
If the real goal here isn't maximum confidence, but accurate confidence, a system that's engineered to know its own limits, how does that new transparency change the professional and ethical responsibility of the human who's relying on its output? That's the critical link we now have to define.